This is part one of an explanation of how to use Newton's second law. So the steps are pretty much out of your book. Establish a coordinate system, draw a free body diagram, and again focus on contact and non-contact forces. As I mentioned in class, the non-contact force that's going to be prevalent in our problems is the gravitational force. A motion diagram is helpful to remind you of what the direction for delta V is, because the direction for delta V is the direction for the acceleration, and from Newton's second law, the direction for the acceleration is going to be the direction for the net force. Thirdly, write Newton number 2 in vector form. And 4, from the force diagram, you can now read the force components and write Newton number 2 in component form. And step number 5 is solve the equations, I should say. So let's take an example. Let's say, this is from your book, a 1,500 kilogram car is pulled by a tow truck. The tow rope tension is 2,500 newtons, but there's also a 200 Newton frictional force that opposes the motion. The car starts from rest. What is the car's speed after 5 seconds? Okay, so the motion diagram is going to be one of the car picking up speed, here's the coordinate system. I'm assuming the standard y up, x to the right, positive direction for the two axes. And my free body diagram now, I have four forces acting on this car. F sub g vector, that's the attraction of the Earth on the car, which is its weight and magnitude. That's going to be m times g. The normal force, it's touching the road, so there's an upward normal force on this car. The tension force from the tow rope, and then the smaller frictional force acting to oppose the motion. And I'm assuming the car is moving rightward, so the T is going to be parallel to the acceleration, and the frictional force is going to be anti-parallel to the acceleration that we know this car has. So the vector equation for this problem is the sum of all the vectors. N vector plus T vector plus F sub G vector plus F vector is equal to the mass times the vector acceleration, and that's going to be equal to the net force. But T vector is equal to T times I hat. F sub G vector is equal to minus mg times j hat. F, the frictional force, is minus F times I hat. And N is equal to, N vector is equal to the magnitude of N times j hat. So now I can write the x component as T minus F is equal to M times A sub x. So what goes in here are the components of the vectors from the vector equation. And then the y component equation is N minus mg equals m times A sub y. So if you look at the x equation, there's no if you look at the x equation, there's no there is no normal force or gravitational force, because those only have y components. And if you look at the y component, there's no t or f because they have no y component. So taking the equations one at a time, I can solve the x component equation for A sub x. That's T minus F over m. 2,500 newtons minus 200 newtons over 1,500 kgs. And so the x acceleration is 1.53 meters per second. This could have a plus or a minus sign. Here, this is a plus sign, which means it's accelerating in the positive x direction. So the y acceleration in this problem is 0, and so the y equation to finish this up, even though it's not required for the question that's posed. A sub y would be 0, which means n minus mg would be 0, and therefore n is equal to mg. All right, so continuing on with the x solution. A sub x is 1.53 meter per second, so we can now use the first kinematic equation, knowing that the car started from 0, to state that Vx is equal to A sub x times t. 1.53 meters per second times 5 seconds is 7.7 meters to 2 sig figs. I might as well go to the second part of this. So let me go ahead and go to the second part. Let's do another example. Again, this is from your book. A half a kilogram rocket is launched up. The rocket motor provides a thrust of 20 newtons for 5 seconds. That's fairly typical for a model rocket. What is the max altitude? Ignore any mass loss, which is in fact occurring as it uses its fuel up, and ignore air resistance, which is ignoring air resistance is definitely not probably a very good assumption for as fast as this rocket is probably going. But we will nevertheless do that. Okay, so here's my choice of coordinate systems. Essentially, there are two legs to this, and I didn't maybe draw the motion diagram quite big enough, but there's two legs. There's a launch, a boost phase, let's say, where the motor is on and you have acceleration in the upward direction. But then when the motor cuts off, the rocket will coast up to its max altitude, and during that second leg, the acceleration is down. So during the first leg, you have a net upward acceleration by Newton's second law, and during the second leg, you have a downward net force because the acceleration is down. Net force up in the beginning, net force down at the end. So when the motor is on, the vector equation would be the thrust of the rocket, the vector force of that, plus the vector force for gravity is equal to m times the vector acceleration. But we can split that up into a y direction. There really is no x direction to talk about in this. And so the y component for s sub t for ft vector is ft, and for fg vector is minus mg. So ft minus mg is equal to m times ay. Ay is ft minus mg over m. So now we can put the numbers in. 20 newtons minus 0.5 kgs times 9.8 divided by 0.5 kgs. That gives 30.2 meters per second. And now I can find the delta y the rocket has upward displacement during the boost phase, which is 1/2 times 30.2 meters per second times 5 seconds squared. That's 377 meters. Now the motor is off, and so in that second case, we have this second free body diagram here. In the y direction, the Newton's second law is minus mg equals m times ay. And so therefore a sub y is equal to minus g. And Vy naught from the boost phase is, using the first kinematic equation, is 30.2 meters per second, the acceleration we solved for up above, times 5 seconds. And so it starts the second phase here with an initial velocity of 151 meters per second. And so what we can now do is we can figure out what the additional displacement is during that second phase. I'm going to use kinematic equation number 3, which gives me 1160 meter displacement during the second phase. So since I got a upward displacement of 377 meters, I can take that as a y naught for my second phase. The maximum height of the rocket is going to be the height at the end of the first phase, 377 meters, plus its additional displacement upwards during the glide phase, 1160. So that comes out to be 1540 meters. And that's a nice little problem. It shows you how you can apply Newton number 2, use the constant acceleration kinematic equations when we have two separate types of motion.